This video is brought to you by Hackerama Chalk. Use code TPSA 10% off to get a discount. So now we can move on to defining continuity. We'll start with just revising it in one variable, which should look familiar from a calculus course, and then we'll move on to the multivariable case. So if we just take two subsets of R, A, and B, and have a function f which maps from A to B, we call it continuous at a certain point P in A if given any epsilon greater than 0, so normally we take epsilon very small, we can find some positive delta such that this holds true. So for any point x in this interval, so P take away the delta and plus a delta, intersection with A, this part is just because we want it, we want x to actually be within A. We want this to imply that f evaluated at that x is within f at that point P, take away that little epsilon plus a little epsilon. So we can see that in action here. If we have just some function f, it's continuous, which it should just look continuous, there just shouldn't be any obvious breaks. We can take epsilon here, right? And we can kind of draw two lines across and two lines down, and then this should be the delta that we take, because for any x between here and here, so between p minus delta and p plus delta, for any x in here, f of x, that's all these values in there, will lie within f of p plus epsilon and f of p minus epsilon. So therefore we can say p, which just lies somewhere in the middle, f is continuous at p. And if f is continuous at all points p within A, we say f is continuous at A. And here is a function g, very obviously not continuous, because if we took epsilon to be this small here, if we sort of ran that size up and down the length of the graph, we could find this obvious gap here, where no matter what delta we took, we would never be able to ensure that the g evaluated at this point here would either come to there or there and wouldn't actually lie in between these two lines here. This will be discontinuous. Now the multivariable case should be similar. If you want to just set the dimensions to 1 and convince yourself that these two things are equivalent. If we take x as a subset of Rd and y as a subset of Rb and f a function mapping x to y, we call that continuous at a point P in x if for any epsilon greater than 0, there exists a delta greater than 0, such that for any point within x which satisfies that x is within a delta of p, then f evaluated at that x is within an epsilon of f evaluated at that point p. So when the dimensions are 1 in x and y, this just means that we're plusing or minusing a delta from p. And here, we're plusing or minusing an epsilon from f of p here. So it's the same thing. This is just the generalized version. And again, if f is continuous at every point within x, we say it's continuous on x. So here we have x, some set in R2, and here we can draw the ball centered on P, a radius delta, and here we can draw the ball, the y ball centered on f of P, a radius epsilon. And again, we should be able to take epsilon in theory as small as we want. Let's say f maps this ball to some strange set here. Shouldn't map balls to balls in generality. So it's mapped to this strange set here. But as long as that set is contained within this ball of radius epsilon in y, then we're all good. It should be continuous. So as I say, we choose any epsilon. So we set epsilon first. The epsilon could be really small. So that in general should just mean that we have to take delta to be, small, or maybe we have to take delta to be large, but just so that when it transforms this ball under f, that f of that ball, of that x ball, should shrink down to be contained within epsilon. And if we can't do that, then if we can't find such a delta at that point, then it's not continuous at that point, in much the same sort of idea behind this one. So now an example of a discontinuous function would be, let's say, if we had in x this circular on the point P, right, which we want to check if it's continuous at. So in y, we have g of P, and we draw our circle of radius epsilon. Now let's say we chose a delta, right, where this was our circle of radius delta, and this shaded area here gets sent to this patch, and this non-shaded area gets sent to this patch here. Well, this would be a discontinuous function, right? Because what we want is that the behavior around each small patch of our point P be sent to just around our point P. And we can see here, we can imagine that this shaded area gets arbitrarily close to P. So we wouldn't be able to take any delta neighborhood around P without getting some of that patch in it, which would be sent to very far away from G of P. So if then for small epsilon, this wouldn't work. So even for this epsilon here, we can see that we get two patches that are not contained within the circle. So therefore, this would be discontinuous. So the idea is that, this patch here will be kind of cut in two, and this part will be pasted over here, and this part will be pasted over here, which is not allowed. So some properties of continuous functions, which you've probably seen before, is if we have f mapping between x to y and g from y to x, if f is continuous at p and g is continuous at f of p, then the composition map g of f, which maps from x to z, is continuous at p, which should seem intuitive enough. Now, if we have a sequence in x which converges to a point P and a continuous map f between x and y, then the continuous map f will preserve the convergence of that sequence. So each point x1, x2, f of those points should converge to f of p in y. Now, when you're working with multivariable functions, you've probably seen in multivariable calculus that you can write them as their what we call components. So if x is d-dimensional and r is b-dimensional and f maps from x to y, we can write f as f1, f2, all the way up to fb, with each fi mapping from x just to r, because rb is just b Cartesian products of R. So we can just see what it does in each one of those dimensions. And each one of these F1, F2, FB, these are all the components of F. And if F maps from X to Y, if we want to check the continuity at P, that is completely equivalent to checking the component of each Fi, each component at that point P. So an example would be this function here, which maps R2 to R, which just adds the components x and y. So we can show that this is continuous. So just take any point x, y in R2 and let any positive epsilon. And we're going to say that delta equal epsilon over 2 will work. So if we were to take any random u and v in R2 that lies within a delta from x and y, then these two inequalities would hold. They'd both be within delta of it. So then we can just look at the distance between the functions evaluated at these points then, and because it's within the delta, we want these to be within an epsilon of each other. So we just plug in what those functions actually evaluate to, and then because of the triangular inequality, we get this inequality here, which because we've set, we have this here, we have that this is strictly less than 2 delta, and delta equals epsilon over 2, so it just equals epsilon. So we get our strict inequality from here. So it is less than epsilon, so it's continuous at that point xy, but xy was arbitrary, so it's continuous on the entirety of R2. Now there's some very nice properties here of functions. So if x is any subset of Euclidean space and f maps x to R and g maps x to R, so not like R D or RB or anything, and if they're both continuous on x, then the following properties hold. You can add them, subtract them, multiply them, and if g is non-zero in the entirety of x, you can take a quotient. And all of these operations mean that they makes a new continuous function. So it can, if like you get a bit of a field of continuous functions. Now from this, it makes it really easy to check which functions are continuous. We'd have that this is continuous kind of by default because the identity xy to x and xy to y, both of those would be obviously continuous, and then just the sum of them would be continuous. And without even checking much at all, we can just check that this function here, g, is continuous. So it maps R2 less the origin to R3. We can just look at each component then and see this is a quotient, this is a quotient, and this is a product. So both of the functions in this product, cosine y are continuous. Cosine y is clearly continuous. The tops of these fractions are both continuous, cosine and sine, and the bottoms we can divide, they're continuous as well because x is continuous, so x squared as a product is continuous. Same with y, you can add them, again continuous. And the only potential issue would be when the bottoms are 0, but that can only happen at the origin, and we're excluding the origin, therefore g is continuous on this punctured plane. Now, as an exercise, you can try and prove this. If f maps x to y, where x is a subset of Rd and y is a subset of Rb, and f is continuous. If we have a different function, g, going from x to y, prove that that's continuous, where g is just of the form g of x is just the norm of f of x. And this actually ends up being a very nice proof. Now, for this theorem here, it relates open sets back to continuity, which is actually a way that we can, this is how we normally define continuity when we come at it from a topological viewpoint. So here, if we have x, subset of Rd, y of Rb, and f a map between them, it's continuous if and only if its pre-image of V is open in x for every V it's open in y. So again, this is the pre-image, not an inverse. This works for any map. And just recall, pre-image, this is just a set of points in x which map to V under f. So you should be able to take any open V in y, look at its pre-image, and it should stay open in x. So an example of this in action, if we just take any continuous function from R to R and consider this set here U, which is the points where f is positive, and look at this open interval here, V, then we can just write U in terms of the points in R where f is in V. This is actually just the pre-image of V, the set U. And because we know that V is open, just an open interval, then and f is continuous, then its pre-image of V under f is open. That means that U is open. So this set here, even though f, we have no other restrictions on f other than it's continuous, this set actually is open. This set might be disjoint. If a function sort of went up and down below the origin, or below like y equals 0 a lot, it mightn't be obvious that it is that this set where it's just positive is open, but it actually always is, as long as that function is continuous. Now we can use the converse of the statement in this exercise here. So if f is mapping from R to R, and we have f as this function here, so x when x is negative, and x squared plus 1 when x is greater than or equal to 0. And this is how it looks like here. We're traveling up, and then we have a discontinuity here at 1, or sorry, at 0. It jumps from 0 to 1, and we continue on. And we want to show that this is discontinuous using open sets. So just take V to be the interval I chose 0 to 5. And we look at the pre-image of V. But that's just a set of points in R where f of x evaluates between 0 and 5, which, if we look at the piecewise definition, that's a set of negative points where x is between 0 and 5, union the set of positive points where x squared plus 1 between 0 and 5. Now here, if x is strictly less than 0, x is strictly greater than 0, it's contradiction, it's a null set. So we drop that and just focus on this set here. So x is positive and x squared plus 1 strictly lies between 0 and 5. And you can simplify that a bit and you'll find that the only answers to that lie in here. 0 to 2, 0 inclusive, which is not open. So the pre-image of an open set wasn't open. That means it was not continuous. So it violates this side of the theorem. So just some important examples which kind of crop up often is that if we just took x as a subset of Rd and f mapping x just to the real numbers as continuous, then the set where the function is below a certain constant, above a certain constant, or sandwiched between two constants, each time with strict inequalities, they're all open. Now, if we were to replace these two with non-strict inequalities, and take the case where the function just equals a single value, so this would be a line, these are all closed. Now we can look at the multidimensional case of the extreme value theorem, which just says if we have a non-empty subset of Euclidean space that's closed and bounded, and this condition is important, if we had this subset x and take a continuous function of f mapping to the real numbers, and the reason we're mapping to the real numbers is because if we were mapping to R2 or something like that, we don't really have a notion of height in those spaces. You can't fully order those as we're about to do here. So if we meet these conditions, there's two values, or at least two values, a and b, in our set x, for which all values of a function will lie between those two. Essentially, we can find a maximum and a minimum. So here on this closed and bounded set of R2, if we were mapping to R on this axis here, we'd have some strange shape, and just drawn in the lowest point and the highest point, f of a and f of b, and all the other values are intermediate. Now we can define what it means to be uniformly continuous in the multidimensional case. So again, take x as an Rd subset and let f map to Rb. So we'll call f uniformly continuous if for all epsilon greater than 0, there can exist a delta greater than 0, such that for any 2 points in x, if they're within a delta of each other, that will imply that when evaluated at f, those values will lie within an epsilon of each other. So we want 2 points here, any 2 points which are close enough, the epsilon which will be given, then we should be able to find some delta, which means that once we only consider points that are a delta apart, then they will map under f to be an epsilon apart. And actually, this choice of delta should be fully independent of your points x and y. So an example of a function which is not uniformly continuous would just be x squared. So let's say it was uniformly continuous, then we'd be able to find a delta such that this is always true. When 2 points within a delta, then when we evaluate them to x squared and y squared, they're going to be within an epsilon. Well, we just consider the case where x equals y plus delta over 2, and we'll only take the y to be positive. So we want epsilon to be greater than x squared minus y squared, and just difference of 2 squares. And then we're going to sub in our value of x here, and these two y's cancel. Delta over 2, we want delta to always be positive, so that's going to come outside of our absolute value. And then this quantity here is always strictly greater than delta y, and we can do that because we're considering y's to be greater than 0. So now if we follow this from here to here, we can say that epsilon is greater than delta y, but for the case that y equals epsilon over delta, which is fine because we're So considering that y's are positive, both of these are positive. We sub in for here, and we'll get epsilon is strictly greater than epsilon, not true. So f is actually not uniformly continuous. So just two more. If a function is uniformly continuous, that implies continuous. So uniform continuity is a stronger condition. And if we have x in Rd, which f which maps x to Rb, if we require that x is non-empty, closed, and bounded, so the same conditions as the extreme value theorem, and f is continuous, then on x, f is also uniformly continuous.